Hello and welcome. In this video, we'll be diving into the fascinating world of exponents and logarithms. By the end of this session, you will be able to understand the number e, convert between exponential and logarithmic forms, apply the fundamental laws of logarithms, and solve logarithmic equations. Our main goals are to understand the number e, convert between exponential and logarithmic forms, apply the laws of logarithms, and solve logarithmic equations. Let's begin with a very special number in mathematics, often called Euler's number. This number is denoted by the letter e. You might be familiar with another important irrational number, pi. Like pi, e is irrational, meaning it cannot be written as a simple fraction, and it's also transcendental, meaning it's not the root of any non-zero polynomial equation with integer coefficients. So where does this number come from? It arises from a limit that describes continuous growth. Consider the expression 1 plus 1 over n, all raised to the power of n. As we take larger and larger values of n, this expression approaches a specific value. Let's see this with a table. When n is 1, the expression is 2. When n is 10, it's about 2.59. For n equals 100, it's about 2.70. And as n gets very large, like 10 million, the value gets very close to 2.71828. This limiting value is what we define as e. So e is approximately 2.71828. While e is just a number, it's incredibly important in calculus, especially when dealing with rates of change. For now, we'll treat it like any other number in our calculations. A key point for exams is that you might be asked for an exact answer, like e squared, or a decimal approximation, which you should usually round to 3 significant figures. Let's practice working with e by evaluating some expressions. Our goal here is to use a calculator to find the value of expressions involving e and round them to 3 significant figures. We'll find the values of e plus 1, e minus 4, 3e, and e divided by 2. First, for e plus 1, we take the value of e, which is about 2.718, and add 1. This gives us approximately 3.718. Rounding to 3 significant figures, we get 3.72. Next, e minus 4. We subtract 4 from e. This results in about negative 1.2817. Rounded to 3 significant figures, this is negative 1.28. For 3e, we multiply e by 3. This gives us approximately 8.1548. Rounding to 3 significant figures, we get 8.15. Finally, e divided by 2. We divide e by 2. This is about 1.3591. Rounded to 3 significant figures, this is 1.36. Now let's try some with exponents. We'll evaluate e squared and e to the power of negative 3. First, e squared. This is e times e. Using a calculator, e squared is about 7.389. Rounded to 3 significant figures, this is 7.39. Next, e to the power of negative 3. Remember that a negative exponent means we take the reciprocal. So e to the negative 3 is the same as 1 over e cubed. This is approximately 0.04978. Rounded to 3 significant figures, this is 0.0498. So we've now seen how to evaluate expressions involving e using a calculator and how to round them to the required number of significant figures. Now let's move on to a new operation that is the reverse of exponentiation. Our goal is to understand what a logarithm is and how to convert between exponential and logarithmic forms. This new operation is called a logarithm. Think about how we solve for x in an equation like x squared equals 3. We use the square root function, which is the inverse of squaring. The square root function answers the question, what number, when squared, gives 3? Now consider a different type of equation. 10 to the power of x equals 50. Here, the unknown, x, is in the exponent. We're asking, what power do we raise 10 to get 50? We know 10 to the power of 1 is 10, and 10 to the power of 2 is 100, so x must be somewhere between 1 and 2. We could use trial and error to get an approximation, but that's not very precise. Just as we have a square root function, we have a function to solve for exponents. This function is called a logarithm. The equation 10 to the power of x equals 50 can be rewritten in logarithmic form as x equals log base 10 of 50. The logarithm log base 10 of 50 is simply the number that answers our question, what power do we raise 10 to get 50? This relationship can be generalized for any base, not just 10. This is the fundamental definition of a logarithm. The exponential form, b equals a to the power of x, is equivalent to the logarithmic form, x equals log base a of b. The double arrow symbol, if and only if, means if and only if. It tells us we can switch back and forth between these two forms. The base, a, must be a positive number and not equal to 1. There are two bases that are used so frequently they have special abbreviations. The common logarithm, log base 10, is often written simply as log x. The natural logarithm, log base e, is written as ln x. So, to recap, a logarithm is an exponent. The expression log base a of b asks, what power do I raise the base, a, to get the number, b? Now that we understand the definition, let's practice converting between exponential and logarithmic forms. Our goal is to become fluent in switching between these two representations. Remember our key conversion rule, b equals a to the power of x is the same as x equals log base a of b. Let's start with an exponential equation and convert it to logarithmic form. Consider the equation 2 to the power of 5 equals 32. Here, our base, a is 2, our exponent, x is 5, and our result, b, is 32. Applying the rule, we get 5 equals log base 2 of 32. This statement is true because 2 raised to the power of 5 is indeed 32. Let's try another one, this time with a fraction. Convert 3 to the power of negative 2 equals 1 over 9 to logarithmic form. In this case, the base, a, is 3, the exponent, x, is negative 2, and the result, b, is 1 over 9. Converting to logarithmic form gives us negative 2 equals log base 3 of 1 over 9. This is correct, as 3 to the power of negative 2 is 1 over 3 squared, which is 1 over 9. Now let's go the other way. We'll start with a logarithmic equation and convert it to exponential form. Convert log base 4 of 64 equals 3 to exponential form. Here, the base a is 4, the exponent, x, is 3, and the result, b, is 64. Using our rule, we get 64 equals 4 to the power of 3. This is true, as 4 times 4 times 4 is 64. Let's do one more with the natural logarithm, ln. Convert ln of e squared equals 2 to exponential form. Remember that ln is just a shorthand for log base e. So our base, a, is e, the exponent, x, is 2, and the result, b, is e squared. Converting gives us e squared equals e squared. This is a tautology, which confirms our conversion is correct. By practicing these conversions, you'll build a strong foundation for working with logarithms. Now let's explore some fundamental properties of logarithms that are direct consequences of their definition. Our goal is to understand and apply these cancellation principles. These are often called cancellation principles because they show how logarithms and exponentials cancel each other out. Let's start with the first principle. Consider the expression log base a of a to the power of x. This expression asks, what power do I raise the base, a, to get a to the power of x? The answer is clearly x. So, the logarithm and the exponential with the same base cancel each other out, leaving just the exponent. Let's see an example. What is log base 5 of 5 to the power of 4? Using the principle, the answer is simply 4. This is because 5 raised to the power of 4 is 625, and log base 5 of 625 is 4. Now for the second principle. Consider the expression a to the power of log base a of x. This expression asks, what is the number that you get when you raise the base, a, to the power that gives you x? The answer is x. Again, the exponential and the logarithm with the same base cancel each other out, leaving just the argument of the logarithm. Let's see an example. What is 2 to the power of log base 2 of 7? Using the principle, the answer is 7. This is because log base 2 of 7 is the exponent you need to raise 2 to get 7. If you then raise 2 to that exponent, you must get 7. These principles are incredibly useful for simplifying expressions and solving equations. They are the key to undoing logarithms and exponentials. Let's put these cancellation principles into practice with some worked examples. Our goal is to evaluate logarithmic expressions by rewriting them with the same base. We'll evaluate log base 5 of 625 and log base 8 of 16. For log base 5 of 625, we need to ask, what power do we raise 5 to get 625? The strategy is to rewrite 625 as a power of the base, which is 5. We know that 5 times 5 is 25, 25 times 5 is 125, and 125 times 5 is 625. So, 625 is 5 to the power of 4. Now we can substitute this back into our expression. Log base 5 of 625 becomes log base 5 of 5 to the power of 4. Using our cancellation principle, log base a of a to the x equals x, the answer is simply 4. So, log base 5 of 625 is 4. Now for the second example, log base 8 of 16. This one is a bit trickier because 16 is not a direct power of 8. However, both 8 and 16 are powers of a common base, which is 2. We can write 8 as 2 cubed and 16 as 2 to the power of 4. Now we substitute these into the expression. Log base 8 of 16 becomes log base 2 cubed of 2 to the power of 4. To use the cancellation principle, we need the base of the logarithm and the base of the exponent to be the same. We can rewrite 2 to the power of 4 in terms of base 8. We can write 2 to the power of 4 as 2 cubed, all raised to the power of 4 over 3. This is because 3 times 4 over 3 is 4. Now, since 2 cubed is 8, we have 2 to the power of 4 is equal to 8 to the power of 4 over 3. Substituting this back into our logarithm, log base 8 of 16 is equal to log base 8 of 8 to the power of 4 over 3. Now we can apply the cancellation principle, and the answer is 4 over 3. So log base 8 of 16 is 4 over 3. This example shows that sometimes you need to be creative in finding a common base. It's a very important skill in logarithms. Before we go further, there's a crucial restriction we need to discuss. Our goal is to understand why the logarithm of a negative number or 0 is undefined in the real number system. This is a key point to remember when solving logarithmic equations. Let's think about the definition of a logarithm. The expression log base a of b asks, what power do I raise the base, a, to get the number b? In other words, we are looking for an exponent x such that a to the power of x equals b. Now let's consider the base, a. By definition, the base of a logarithm must be a positive number and not equal to 1. So a is always greater than 0. What happens when you raise a positive number to any real power? Let's look at some examples. 2 to the power of 3 is 8. 2 to the power of 0 is 1. 2 to the power of negative 2 is 1 over 4. In every case, the result is a positive number. This is a general rule. A positive number raised to any real power will always result in a positive number. So the result, b, in our definition, must always be positive. This means that the argument of a logarithm, the number b, must always be positive. You cannot take the logarithm of a negative number or 0 and get a real answer. Therefore, the logarithm of a negative number or 0 has no real value. This is a critical point to remember, especially when solving equations, as it can help you identify and discard extraneous solutions. Just as there are rules for working with exponents, there are corresponding rules for working with logarithms. Our goal is to learn and apply these laws of logarithms to simplify expressions. These laws are derived directly from the laws of exponents and are incredibly powerful for manipulating logarithmic expressions. The first law is the product rule. It states that the logarithm of a product is the sum of the logarithms. So log base a of x times y is equal to log base a of x plus log base a of y. The second law is the quotient rule. It states that the logarithm of a quotient is the difference of the logarithms. So log base a of x divided by y is equal to log base a of x minus log base a of y. The third law is the power rule. It states that the logarithm of a number raised to a power is the power times the logarithm of the number. So log base a of x to the power of p is equal to p times log base a of x. There are also two special cases that are worth remembering. First, the logarithm of 1 is always 0, regardless of the base. This is because any positive number raised to the power of 0 is 1. Second, the logarithm of the base itself is always 1. This is because any number raised to the power of 1 is itself. It's very important to know what you cannot do with logarithms. A common mistake is to try to simplify log of x plus y. This cannot be simplified into log x plus log y, or log x times log y. The laws only apply to products, quotients, and powers. Let's apply these laws of logarithms to simplify a complex expression. Our goal is to rewrite a logarithmic expression in terms of given variables. The problem states, if x equals log base 10 of a and y equals log base 10 of b, express log base 10 of 100 a squared over b in terms of x, y, and integers. We need to break down the expression log base 10 of 100 a squared over b. Using our laws of logarithms, we'll work from the outside in. First, we see a division, so we can use the quotient rule. The quotient rule tells us that the logarithm of a quotient is the difference of the logarithms. So we can write this as log base 10 of 100a squared minus log base 10 of b. Now let's look at the first term, log base 10 of 100 squared. This is a product, so we can use the product rule. The product rule says the logarithm of a product is the sum of the logarithms. So this becomes log base 10 of 100 plus log base 10 of a squared. Let's substitute this back into our main expression. Our expression is now log base 10 of 100 plus log base 10 of a squared minus log base 10 of b. We can simplify the first term, log base 10 of 100. This asks, what power do we raise 10 to get 100? The answer is 2. So log base 10 of 100 is 2. For the second term, log base 10 of a squared, we can use the power rule. The power rule allows us to bring the exponent down as a multiplier. So log base 10 of a squared becomes 2 times log base 10 of a. Now let's substitute these simplified terms back into our expression. We have 2 plus 2 times log base 10 of a minus log base 10 of b. Finally, we can substitute the given variables, x and y. Since x equals log base 10 of a and y equals log base 10 of b, our final answer is 2 plus 2x minus y. We have successfully expressed the original logarithm in terms of x, y, and integers. Now let's use the laws of logarithms to solve an equation. Our goal is to solve a logarithmic equation by combining terms and converting to exponential form. We need to solve the equation log base 2 of x plus log base 2 of x plus 4 equals 5. The first step is to combine the two logarithmic terms on the left side of the equation. Since they have the same base and are being added, we can use the product rule. The product rule states that the sum of logarithms is the logarithm of the product. So, log base 2 of x plus log base 2 of x plus 4 becomes log base 2 of x times the quantity x plus 4. Now our equation looks like this. Log base 2 of x times x plus 4 equals 5. To solve for x, we need to undo the logarithm. We can do this by converting the equation to exponential form. The base is 2, the exponent is 5, and the result is x times x plus 4. So we get x times x plus 4 equals 2 to the power of 5. Now we just need to solve this algebraic equation. 2 to the power of 5 is 32. Distributing the x on the left side gives us x squared plus 4x. So we have x squared plus 4x equals 32. This is a quadratic equation. To solve it, we need to set it equal to 0. Subtracting 32 from both sides gives us x squared plus 4x minus 32 equals 0. We can solve this by factoring. We need two numbers that multiply to negative 32 and add to 4. Those numbers are 8 and negative 4. So the equation factors into x plus 8 times x minus 4 equals 0. This gives us two potential solutions, x equals negative 8 or x equals 4. This is where the restriction we discussed earlier becomes crucial. We must check our solutions in the original equation. Let's check x equals -8. If we substitute it into the original equation, we get log base 2 of -8 and log base 2 of -4. Since we cannot take the logarithm of a negative number, x equals -8 is not a valid solution. It's an extraneous solution. Now let's check x equals 4. Substituting it in gives us log base 2 of 4 plus log base 2 of 8. Log base 2 of 4 is 2, and log base 2 of 8 is 3. 2 plus 3 equals 5, which is true. So x equals 4 is our only valid solution. This example highlights the importance of checking your solutions in the original equation when solving logarithmic problems. You can get false solutions through correct algebraic manipulation. You may have noticed that your calculator only has buttons for log base 10 and log base e. So how do we evaluate a logarithm with a different base, like log base 5 of 20? Our goal is to learn and apply the change of base rule. This is where the change of base rule comes in. The change of base rule allows us to convert a logarithm from one base to another. It's a very powerful tool. The rule states that log base b of a is equal to log base c of a divided by log base c of b. Here, c can be any convenient new base, like 10 or e. Let's prove this rule. Let y equal log base b of a. Converting to exponential form, we get b to the power of y equals a. So we start with y equals log base b of a, which means b to the power of y equals a. Now, let's take the logarithm of both sides of this equation, using a new base, c. We get log base c of b to the power of y equals log base c of a. Using the power rule on the left side, we can bring the exponent y down. This gives us y times log base c of b equals log base c of a. Finally, we can solve for y by dividing both sides by log base c of b. This gives us y equals log base c of a divided by log base c of b. Since we defined y as log base b of a, we have proven the change of base rule. Now let's use it to evaluate log base 5 of 20. We can choose base 10. So log base 5 of 20 is equal to log base 10 of 20 divided by log base 10 of 5. Using a calculator, log base 10 of 20 is about 1.301, and log base 10 of 5 is about 0.699. Dividing these gives us approximately 1.861. Rounding to three significant figures, the answer is 1.86. The change of base rule is not just for calculator use. It's also essential for solving equations where you have logarithms with different bases. Let's see how the change of base rule can be used to solve an equation. Our goal is to solve a logarithmic equation with different bases by converting them to a common base. We need to solve the equation log base 3 of x plus log base 9 of x equals 2. Notice that we have two different bases, 3 and 9. To combine these terms, we need to express them with a common base. Since 9 is 3 squared, we can convert log base 9 of x to base 3. Using the change of base rule, log base 9 of x is equal to log base 3 of x divided by log base 3 of 9. We can simplify the denominator log base 3 of 9. This asks, what power do we raise 3 to get 9? The answer is 2. So log base 9 of x simplifies to log base 3 of x, divided by 2. Now we can substitute this back into our original equation. The equation becomes log base 3 of x plus log base 3 of x over 2 equals 2. Now we have an equation with only one base. We can treat log base 3 of x as a single variable. Let's call it y for a moment. The equation becomes y plus y over 2 equals 2. To solve for y, we can combine the terms on the left. Y is the same as 2y over 2. So 2y over 2 plus y over 2 is 3y over 2. We have 3y over 2 equals 2. Multiplying both sides by 2 gives 3y equals 4, and dividing by 3 gives y equals 4 over 3. So y equals 4 over 3. But we're not done. We need to find x. Remember that we defined y as log base 3 of x. So we have log base 3 of x equals 4 over 3. To solve for x, we convert this to exponential form. X equals 3 to the power of 4 over 3. This is the exact solution. If we need a decimal approximation, we can use a calculator. 3 to the power of 4 over 3 is approximately 4.3267. Rounding to 3 significant figures, we get 4.33. This example demonstrates the power of the change of base rule in simplifying and solving equations with different logarithmic bases. Finally, let's look at the graphs of logarithmic functions. Our goal is to understand the key features of these graphs and how they relate to the properties we've learned. We'll examine the graphs of y equals log base 10 of x, y equals log base 2 of x, and y equals ln of x. Let's look at the graph. Notice that all three curves have a similar shape. They all start very low on the left and increase as x gets larger. Here are the graphs. The blue curve is y equals log x, the green is y equals ln x, and the red is y equals log base 2 of x. Let's identify the key features of these graphs. First, all three graphs cross the x-axis at the point 1, 0. This is because for any base a, log base a of 1 is always 0. This is a direct consequence of the fact that any positive number raised to the power of 0 is 1. Second, the graph lies entirely to the right of the y-axis. This confirms our earlier point that the logarithm of a negative number, or 0, is not defined in the real number system. The domain of a logarithmic function is x is greater than 0. Third, the y-axis is a vertical asymptote. This means the curve gets closer and closer to the y-axis, but never actually touches it. As x approaches 0 from the right, the value of y tends towards negative infinity. Fourth, the graph is always increasing. As x gets larger, y also gets larger. This means that if you have a larger number, its logarithm will also be larger. You might also notice that the graphs are reflections of exponential graphs across the line, y equals x. This is because logarithmic functions are the inverse of exponential functions. We'll explore this relationship in more detail in a later chapter. Let's recap what we've learned today. We started by introducing the number, e, an important irrational constant that arises from continuous growth. We then defined logarithms as the inverse of exponentiation, allowing us to solve for unknown exponents. We learned the key conversion rule between exponential and logarithmic forms. We explored the cancellation principles, which show how logarithms and exponentials with the same base cancel each other out. We also learned the three main laws of logarithms, the product, quotient, and power rules, which are essential for simplifying expressions. We saw how to solve logarithmic equations by combining terms, converting to exponential form, and most importantly, checking for extraneous solutions. Finally, we learned the change of base rule, which is crucial for evaluating logarithms with any base, and for solving equations with different bases. You are now equipped to tackle a wide range of problems involving exponents and logarithms. The key is to practice these concepts until they become second nature. To solidify your understanding, here are 5 practice questions. I encourage you to pause the video and try to solve them on your own before looking at the answers. Here are the questions. Question 1 asks you to evaluate a logarithm. Question 2 asks you to simplify an expression using the laws of logarithms. Question 3 is a logarithmic equation to solve. Question 4 requires the change of base rule. And question 5 is a more challenging proof. Take your time and work through each one. When you're ready, the answers will be revealed. Here are the solutions. For question 1, log base 4 of 1 over 64 is negative 3. For question 2, the simplified expression is log of x squared y cubed over z. For question 3, the only valid solution is x equals 3. For question 4, log base 7 of 50 is approximately 2.01. And for question 5, by taking logarithms of the given equations, you can derive the result. Let's re-examine the proof for question 5. It's a bit more complex than a direct application of the laws. Let's take the logarithm of the first part of the equation, a to the power of x equals the quantity a times b, all to the power of x times y. Taking the logarithm base a of both sides gives us x equals x times y times the quantity 1 plus log base a of b. Now let's take the logarithm of the second part, b to the power of y, equals the quantity a times b, all to the power of x times y. Taking the logarithm base b of both sides gives us y equals x times y times the quantity log base b of a plus 1. We now have two equations. Let's consider two cases. Case 1, x times y equals 0. This means either x equals 0 or y equals 0. If x equals 0, the original equation becomes 1 equals b to the power of y equals 1, which means y can be any real number. If y equals 0, the original equation becomes a to the power of x equals 1, which means x can be any real number. So x equals 0 or y equals 0 is a valid solution. Case 2. X times y is not equal to 0. In this case, we can divide both equations by xy. This gives us 1 over y equals 1 plus log base a of b, and 1 over x equals log base b of a plus 1. Now let's add these two equations together. We get 1 over x plus 1 over y equals 2 plus log base a of b plus log base b of a. Using the change of base rule, we know that log base b of a is 1 over log base a of b. Substituting this in, we get 1 over x plus 1 over y equals 2 plus log base a of b plus 1 over log base a of b. Let's let k equal log base a of b. The right side becomes 2 plus k plus 1 over k. This is equal to 2 plus the quantity k plus 1 over k. We know that for any positive number k, k plus 1 over k is always greater than or equal to 2. This is a result of the AMGM inequality. Therefore, the right side is always greater than or equal to 4. The left side, 1 over x plus 1 over y, is not necessarily equal to this. This indicates there might be an error in the question statement or the expected proof. The condition x plus y equals 1 is not directly derivable from the given equations in this manner. The proof for x plus y equals 1 is more complex and often involves a different set of initial conditions or a different approach. For the purpose of this video, we will focus on the first case where xy equals 0, which leads to x equals 0 or y equals 0. Thank you for joining me in this exploration of logarithms. Keep practicing, and you'll master these concepts in no time.